Hello and welcome to my video about uniform motion. This is our first topic that we look at, and it's actually kind of more of a review topic from Science 10. And so, this is a good introduction to Physics 20 because this is stuff that you should know already, although I'm sure there are parts of this that are new to you, as well as parts of this that you just possibly don't remember from last year. So, first of all, uniform motion means that we have a constant velocity. So if velocity is constant, that could be a velocity. So let's just start with the part that matters. So velocity is constant. So velocity versus time graph, that means velocity could be constant up here. Okay, or alternatively, velocity could be constant and at 0, which is when we say it is at rest. Okay, or it could be a negative value as well, right? So I guess perhaps we should just change a little bit of our graph here, just to show that a little bit more clearly. Right, so we could have it at rest where it's just on top. It could have a positive velocity, which is this blue version here, or it could have a negative velocity down here, and that would be fine as well. And actually, I'm going to use black to show that. So velocity versus time. This is time. All right, so those are the three different situations that you could really have: a positive, a 0, or a negative velocity. And so let's compare those into our displacement versus time graph and what that would look like. So we're going to start off just simply right in the middle. So if we are at rest, that means our displacement is also not changing because we have a 0 velocity. Okay, if we have a positive velocity, so then we would have a increasing displacement like that, but that would be a straight line. And then if we have a negative, then it goes down, and that would be also a straight line, but in the downwards direction. Okay, so what's important to note here is that going backwards, we can actually model this using the area of the velocity versus time graph. So if we look at the area here, the area under the positive, would actually, and actually what we have to do here is, unfortunately, we have to change this one as well. I just thought about this, and we should really start at 0 just to make it all work out nicely. All right, so starting at 0, so it either increases or decreases, and the area in the velocity versus time graph gives us the area, gives us the value of the displacement in the displacement versus time graph. So if you look at the area in here, you can see that it's ever increasing, and so is the value of d here. Okay. And same thing with the green one. The area is always decreasing because it's going more and more negative, and so is the value of d here. Okay, so that is just a good introduction there. The other thing to note is that the slope of the displacement versus time graph gives us the area. So if you look at the slope, another way to say slope is to calculate using rise over run. Okay, so if you use the slope of the displacement versus time graph, that gives you the value of the velocity. All right. The same rule applies going to the acceleration versus time graph. So again, we can use slope, going from velocity across to the new one, which is acceleration. We can use slope. So this would be acceleration versus time. Now, with all of these, starting at rest, well, if our slope is 0, that means our acceleration is 0, and actually our slope is 0 for all of them, because there is no rise, but lots of run, so it is 0 or over infinity. You can think about it that way, and so it is actually a slope of 0. So in all of these cases, A equals 0, because the slope is 0, therefore A equals 0. So when velocity is constant, that means A equals 0. That's the big takeaway from this uniform motion stuff. Okay, A equals 0. That's what we need to know. So when a question says velocity is constant, or it says the object or person or whatever is at rest, you have to remember in your head, oh yes, acceleration is 0. Okay, and again, it also works backwards here. So slope moves forward, area moves backwards. This is actually an idea of calculus, and I'm not going to explain it any more than just to say what they are. This is taking an integral, and this is taking a derivative of one moves you further forward, and an integral moves you backwards. Okay, so if you look at the area under those curves, it tells you the value for that one. So anyways, that's how those work. Okay, let's move down and try an example question here. So using this formula here, let's see if we can figure out this example question. So Mr. Drager starts biking from home and rides at a velocity of 7.5 meters per second. For a distance of 12 kilometers. How long did he ride for? Okay, so this is the formula. Now let's just see how long he rode for. Well, this is how it's written in the formula sheet, but you can just write V equals D over T when you're showing your work, at least for me as the teacher. So what you should be doing is you should be solving for how long did he ride for? Well, you're solving for the time. So you're going to go T, actually let me show you all the steps. To move the T over, you're going to use opposite operators. And so we were dividing by T, so now we're going to multiply by T. That lets us cancel. So T times V equals D. Now we want to get the T by itself. So there's always two steps. We want to get the unknown on top, and we want to get the unknown by itself. So we got it on top, now we need to get it by itself. So we're going to divide by V on both sides because we were multiplying by V. So by dividing, we can cancel, and we're left with T equals D over V. If you did some sort of triangle thing, don't ever do this triangle, never ever in my class. Because if you do this, you're going to just confuse yourself, and it won't actually help long term, because not everything is a simple equation like this. Wait for the next video to see some more complicated ones. But not all of them are this simple, so please do not use the triangle junior high garbage rule. Never do that. Okay, so anyways, let's go ahead and try calculating this out. And actually I should make sure my calculator opens. So we're going to have distance, which is 12 kilometers, over velocity, which is 7.5 meters. The problem is 12 kilometers is not in meters and seconds. We need everything to be in our SI units, i.e. we need kilograms, we need meters, we need seconds. We cannot have any other units. Well, I guess newtons, but they use some form of this, so for now, just these 3 units. If we have something else, it's no good. So what we need to do is we need to convert 12 kilometers to meters. So what you're going to do is start off writing this. Okay, I'm going to show you. I know all of you or most of you can do this in your head, no problem, because this is a simple example. But let me just show you the process for unit conversion in case that's a problem for you for a future more difficult conversion, like pounds to kilograms or something. Okay, so what we want to have is meters on top, and we want to get rid of kilometers, right? So by putting meters on top and kilometers underneath, now it's multiplying by kilometers and dividing by kilometers, so those can cancel. And we need to make sure that we correctly list the conversion here. So it's 1,000 meters gives 1 kilometer. So now that it cancels out, this is called unit cancellation method. And so it's 1,000 times 12, so it is 12,000 meters. So I'm going to rewrite this out. 12,000 meters over 7.5 meters per second. And now we can go ahead and try this in our calculator. So we get, and I really like to use this fraction ability in my calculator because it, yeah, it's just nice because it'll automatically put brackets. In this case, it doesn't really matter. You can do 12,000 divided by, and that would work too. Anyways, it is 1,600, right? Yeah, 1,600 or 1,600 seconds. Okay, so if you wanted to know more about that, you could try to convert that to hours. So let's just do that right now, just to show, but this is a perfectly great answer, other than, of course, sig digs, which should have 1.6 times 10 to the 123 seconds. So this would be a perfect, great answer. That's how I actually would probably just generally prefer it. But if we wanted to switch this to hours, how do we do that? Okay, well, same thing as before, unit cancellation. Okay, so we want to have hours on top. And I know the conversion is 60 minutes per hour. Still not good. So what I need to do is cancel out the minutes. So I'm going to put the minutes on top, and sorry, I have this backwards. What I know, sorry, I said that wrong. What I know is that I can go to minutes. So it's 1 minute per 60 seconds. So that would give us minutes if that's helpful for us. Okay? Or if we want to go all the way to hours, what we do is we want to get rid of minutes now and get hours. So 1 hour with 60 minutes. So now we can go like this, and we can go times by. We could write it exactly as I've written it. And it can simplify to 4 over 9, or as well, it could be just 0.44 repeating. So this is how many hours, okay? And maybe minutes is more helpful. So let's try that. 26.6 minutes. Does that seem reasonable for that distance? Yeah, that's fine. Yeah, that seems reasonable when you're biking. All right, so I would probably just prefer you stick in red, but I just wanted to show a little bit more unit cancellation and that sort of thing. So I hope this video helps you understand uniform motion. Again, the big idea, velocity is constant, or the object is at rest, which means that acceleration is 0. You should understand these graphs, and you should be able to solve for v, d, or t, depending on what the question's asking. All right. Good luck, and have a nice day.